In this lab, I examined the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring, mirroring extreme sports activities like canyon rope swinging. I will observe the motion of the swinging mass using the provided video through Tracker, comparing it to a GlowScript-generated model showing the mass's predicted motion. Before I discuss my process and results, I would like to cover the basic fundamental principles that I use to observe the mass's motion. Newton's second law, shown here, was used to describe the mass's position and velocity change as it oscillates back and forth in an arc. Also, since the spring is initially in static equilibrium when the mass is at rest, I was able to apply Hooke's law with the force of gravity to estimate the spring stiffness as well as its relaxed length. Along with that, I used the energy principle to see if the spring mass system's motion satisfied the principle where the change in energy will equal zero as a result of its changes in kinetic, gravitational potential, and spring potential energies. Using the provided video for this lab, I calibrated the rest length of the spring mass system and found the positions of the center of mass for each frame of the mass's movement. Through this, I was able to generate these graphs for the mass's x and y position versus time, which clearly shows an oscillating motion. I took the table values for the x and y positions of the mass and converted it to a CSV file for use in my GlowScript code, which I will discuss now. To start, I edited the initial conditions of the spring mass system to include the mass and initial position and velocity of the hanging mass. Also, I added in the estimated spring constant and relaxed lengths from the accompanied lecture video because the same spring was used in both videos. Following along, I found L to be the distance between the mass and the origin point of the spring, and I used the equations from the fundamental energy principle to initialize the mass's kinetic, gravitational potential, and spring potential energies. For the while time loop, I put the ending time from Tracker as the terminating condition, and I updated the gravitational, spring, and net forces acting on the mass as it moves iteratively. I also applied Newton's second law to the loop to update the mass's position and velocity, along with the energy changes used to satisfy the energy principle. The program generates a graph that compares the observed motion of the spring mass system from the CSV file to the predicted motion of the spring mass system from the code. As you can see, the predicted path of motion in blue is much more clear and fluid because it does not account for the negligible forces such as drag and human error, so the mass moves more coherently. Whereas for the observed motion in red, the mass moves at a larger amplitude and takes into account drag as well as human impulse with the initial push and human error. Also, another reason why the predicted and observed graphs look different is because of their respective time steps, where the code was able to include a much smaller time step and therefore create a much more reasonable looking graph than Tracker. The program also generates a graph to show the energy changes of the spring mass system. The kinetic energy change, shown in blue, opposes the gravitational and spring potential energy changes, shown in red and green, to show that the total energy change, shown in orange, is hovering at around zero. This plays into the first "what does it mean" question, where it asks if the energy principle is satisfied based on the model's motion. I believe that the energy principle is satisfied because the change in total energy of a system is equal to the amount of work done onto that system. Since the mass is simply being released from rest without any initial force, there is no external work being done to the spring mass system, if we include the spring, mass, and earth in the system. Since the mass is oscillating back and forth, the kinetic energy changes oppose the gravitational and spring potential energy changes, satisfying the law of conservation of energy. Therefore, since no external work is being done to the system, the total change in energy should be at around zero, which is shown on the graph here. To answer the second "what does it mean" question, I estimated the periods of oscillation for the x position versus time and the y position versus time graphs from Tracker by finding the average period for all of the oscillations. For the x position, I got an average period of about 1.65 seconds, and for the y position, I got an average period of about 1.5 seconds. The reason why these two periods differ is because in looking at the mass's motion as a whole, there are two components at play. The X motion moves more like an oscillating pendulum, whereas the Y motion moves more like a spring oscillating up and down. Therefore, since the two components follow different oscillating patterns, they will tend to have a different period length as a whole. Thanks for watching.